So just to fill some time, so just very briefly about what cement additives are and try and relate them to how to help the industry utilise SCMs, but also in a roundabout way alternative raw materials and fuels. So the first question I think goes to a lot of businesses: why even bother? Well, why should, in our case, the cement companies even consider using cement additives? You can make cement quite happily without them. In fact, they're not usually needed at all. There is a few exceptions. North America is one market where virtually all the cement uses some kind of chemical agent. It's mainly there as a grinding aid, but mainly to improve the flowability of the cement for distribution purposes. Anyone knows unloading compacted powders, they obtain a cohesive strength, and when you treat them with a chemical in a grinding process, in the case of cement, you actually increase and improve the unloading times. You actually reduce the unloading time from ships, from rail cars, and from road tankers. And of course, you can do the mathematics. It can have an impact on distribution costs. So why do some plants use them? Well, it's quite simple. They've got to be profitable. I'm not ashamed. I'm not really in direct sales, but I'm not ashamed to say that we sell our products to make money. And so the users have to obviously have the economic benefits to justify the cost. And it's all about just finding that value and putting the cost to it, because a lot of the values are qualitative. It does require some knowledge of cement plants and what markets they operate in. It does require some knowledge of the products that we bring to the market. And you're better to do this with quite a professional, systematic evaluation to make it work. So simply put, we're talking about chemical compounds, liquid chemical compounds mostly. They're used in the production of cement mainly to increase the production and the grinding efficiency, but also to directly influence the cement performance, the cement quality. I did just put a little note there. We can also directly apply them to other minerals. They are used in the minerals industry, especially the calcium carbonate industry. And just below, I won't go through them, just some of the brand names, which we don't tend to focus on brand names so much. Basically, our brand is just the company name. So what can additives do? I just mentioned they reduce pack set, so they improve dry flowability. We normally talk about increasing the output of grinding units by anywhere from 5 to 30%. 10% is probably nearer the average. It gives some benefit in grinding efficiency. You end up with a narrower particle size distribution, which gives some performance changes, hopefully most of them beneficial. And we're talking about the chemical agents in number terms for strength, 2 to 10 megapascal increase. Now 10's a lot. If you're talking 28-day strength of 50, 55 megapascals in a mortar, 10 megapascals more is quite significant. So that's the exception rather than the rule, but getting around 10% improvement at 28 days and up to 20% on the early ages is quite feasible. Same for setting time, not talking about trying to make 2 or 3 hours difference, but 10, 20, 30 minutes is quite significant. And also on the water demand, usually the cement producers are playing within the range 2, 3, 4, 5% water reduction, as opposed to when similar chemistries apply to the concrete industry, where you have water reducers right up to the high range, super plasticizers getting 20% or more. I'll just go through the highlighted area. These are really, where can value come from? Value from more output, value from saving energy, spending less money on kilowatt hours per tonne of cement. But just now I'm going to focus on really improving the cement performance gives the cement producer the ability to use more supplementary materials. These supplementary materials tend to affect the cement performance, usually in the strength, especially the early strength, also the setting time. But they have an economic benefit, or they have a different technical target benefit. And the chemical additives can become a part of that to enable them to happen, as long as the benefits are not less than the cost of using the additive. But it also can be applied in the bigger equation within the cement industry of choosing raw materials and alternative fuels. These often have benefits themselves, but may bring less desirable effects or effects that have to be corrected. So maybe bring the two things together, you can save 2x on using your alternative material fuel, but spend 1x to make it happen. And that may be a chemical additive. So the strength enhancing additives are really improving grinding efficiency and also chemically improving strength. And you know, some of the mechanisms are quite well understood. You're going to have to get deep into cement hydration, and some of the presentations yesterday touched on it. It's quite complex in that it's a large science, not a sophisticated rocket science, but it's quite large science. And there's a lot of competing reactions, a lot of reactions taking place, and it's the sum of them all. Like this morning talking about predicting fly ash performance, depends on so many factors. It's the same for cement. But we understand some of the mechanisms enough to be able to choose the right kind of chemical recipes to put together which make our products. And a quick example here with the limestone cement, and yesterday I know we focused on slag and fly ash. In simple terms, slag and fly ash are more expensive than limestone to a cement producer, but they're more beneficial on the cement performance. So actually it's more or less true that the cost per megapascal is much the same whether you use limestone or whether you use slag or fly ash, because the limestone is much cheaper, but it has a much stronger negative effect on your performance. So here we see the ability to achieve a 5% increase in limestone in cases 3 and 4, or in case 4, just comparing to a regular grinding aid. A regular grinding aid is something that's neutral to the cement performance but affects the process performance, whereas the CBA in this case is a quality improver that enhances the cement performance and allowing you to maintain the strength level and putting 5% more limestone, which would be a cost saving to the cement producer. And you know, it's quite simple to do some value model of looking at the benefits. The usual benefits we're looking at are the energy costs. So cement is 30-40 kilowatt hours per tonne, which of course, you know, today's increasing electricity cost has a cost. If you increase the output of a grinding system with more or less the same kilowatts, then your specific energy consumption per tonne of cement is going down. There may be associated repair and maintenance costs with maintaining and running grinding systems. If you make the same volumes in less running hours, you spend less wear and tear on the system. The big saving can be the differential cost between the SCM and the clinker. And in this case, we've also included the CO2 where relevant. I mean, just going across, the idea here was to show taking an untreated cement and comparing to an HEA grinding aid, which is a low cost. This would only, in this case, showing 0.24 euros per tonne of cement to use, but the net savings is only 0.02, so it just about breaks even. But applying an additive at more than double the cost in the ESE CBA column, so this is costing 0.52, but it's now making a net saving of 0.95, a little bit less if I take the CO2 out. The 680,000 there is including 170,000 saving from the CO2. So it's actually justified even without the CO2 in the equation. And here we're only using CO2 at 7 euros per tonne. And you know, there's a lot of debate about the value of CO2 and where that might go. Definitely a topic for another conference. It's sometimes true that when you've got a big differential cost, then you can make savings using additives without taking into account CO2. But we do have cases where the differential cost is less and we can't justify the use of a chemical additive. But if you bring the CO2 into the equation, then you can make a difference. And this was the basis of some of the CDMs that took place where you can apply for credits. So the additives can play a role in, you know, really in helping with choosing alternative fuels, and I'll come on to that in a minute, how using alternative fuels may have a direct impact on the cement performance, which you may need to correct. But the main focus is really on the main theme of yesterday, and that's enabling and facilitating the use of supplementary cementing materials, or non-clinker materials, I think is the best description. Now, when using, you know, the other big area that the industry is focused on, especially for CO2 and cost, is alternative fuels and partially alternative raw materials. But of course, the industry has to think about what influence these could have on environmental emissions, on the process operation, and someone touched on sulfur rings and the like this morning using petcoke, on cement health and safety of the cement itself, of the cement performance, and of course the overall economics of the whole proposition. Now, using additional materials other than limestone and shales can have an effect, and it's the environmental limitations and the process ones that come first, but even if you overcome these, there may or may not be an effect on the final cement performance. And there are minor components. We talked about the waste alumina, phaloxy, was it the name? 70–80% alumina, but it had obviously a few other bits, and it's often the other bits that have to be taken care of. And there's quite a bit understood and not understood. You've got to really understand changes in the chemistry, the crystal size, the morphology, and the structural perfection and imperfections that are in the clinker making. And minor elements are known to inhibit growth or enhance growth of crystals. They can alter the morphology, they can change the melt viscosity, you can decompose crystals. Quite famously, the cement making processes react in lime and silica. You actually make B-lite, C2S first, and then this reacts with excess lime to make C3S. But some minor elements, like phosphorus particularly, which is quite commonplace within the limestone deposits, above a certain level it can stabilise the B-lite so it won't react with the extra free lime, which causes a hell of a lot of problems for the person trying to run a kiln when he sees his free lime is still very high. The effects, of course, vary according to the concentration and the combinations, and also the way the kiln is burnt with the atmospheric conditions. I say the limitations are often imposed mainly because of environmental health and safety, but at the end of the day, some of them will transfer to an effect on the cement performance. And cement performance can be many things. I could probably list you 40 or 50 different topics, but everyone really thinks about the water demand, the setting time, and the strength development. These are the sort of three big areas that we're talking about when we want to translate to construction, to concrete. So, all I'm making the connection today is that you can consider these alternative materials and fuels. If they have an effect on cement performance, then you can bring in the factor of perhaps considering a performance-enhancing chemical additive, which can then hopefully, in an economic way, balance the costs so that you can still overall make a profit from whatever the proposition is. And there's a range of products under different names, and increasingly under quite unadventurous, unbranded names like XS121 or something. Because it leads me to my last point to finish up on, is where are we going with chemical additives? So I didn't give anything about the chemistry. I didn't know if anybody was interested, but glycols and alkanolamines are two of the base chemicals. And you can buy commodity chemicals. The cement producers can use a commodity chemical as a grinding aid. But the more you want to try and achieve in influencing the performance of the cement, usually the more costliest it gets, but the more impact it can have and the more benefits it can bring. And so our business as a formulating chemist is to package chemicals together using multiple ingredients, trying to make a good balance between the cost and the benefits. If the benefits don't exceed the cost or can't be proven to do that, of course the additive won't succeed. But more and more we're really having to go into customization. Every cement plant is a little bit unique in terms of its materials, its process, its markets, it's what it's trying to achieve. And we're seeing more and more being done with additives. Rob said 20 years. I worked in the cement industry before, and the growth of additives is growing faster than cement. In other words, more and more cement is using chemical additives because we're making more and more sophisticated products that give more benefits, and we're operating in quite a diverse, complex environment, more alternative fuels, more different raw materials, greater use of SCMs. It gives more markets for us and more scope for the producers to exploit these. But we're working in quite a noisy, variable environment. On the left-hand side, I've just really gone through the main cement variables. The main chemistry of the silicates, the aluminate and the iron, the alkalis. It's more complex than just the alkali level, it's the total and the water soluble. The sulfate is often just one number, but it's how much is in the clinker, how much is in the cement, what are the forms of sulfate due to the thermal decomposition that takes place in cement production, the fineness of the cement, really the particle size distribution, how the cement, when it's produced, has been pre-hydrated and exposed to moisture and carbonation. It affects the cement performance. The crystallography is a lovely whole area of clinker producing, is understanding the microstructure of what you're making. It's very complex. Of course, the composition of the cement when you're using SCMs and the minor elements. Some of these are quite well studied and quite well understood, but when you bring the multi-variables together, it's not always easy to predict exactly what you're going to get. And on the other side, without going through the whole list, is just the range of some of the real basic chemistry that we use to put together our formulations. And the same applies to us. How do these interact with all these clinker variables? Partly understood, clearly partly not understood. So you can say that we have a bit of a practical trial and error approach, which is true to some extent, but combining a lot of experience, about 80 years in doing this, with a lot of more sophisticated statistical approaches, start putting a little bit of science to it, but at the end of the day, you've still got to do trial and error. So customization, now the procedure we're looking at, is really applying a statistical method to be a bit more systematic in looking at the trial and error. And I won't go through all of this, but anyone who knows statistics, there's a few famous quotes on what statistics is all about, but if you want to look for a small effect, you need to test, and we're talking about physical testing, mortar and concrete, with a lot of practical errors. There's a lot of statistical standard deviation there. So the smaller the effect you want, the lower your standard deviation in your test method better be to see if you've got an effect. So one of the keys to customization is to really minimize your coefficient of variation in your testing environment, which we'll call the noise, because you're looking for a signal. So this signal to noise ratio is incredibly important. If you have a high noise, high standard deviation, and you want to look for a small signal, you've got to do thousands of tests to be statistically confident it's real. So the lower you get the noise, the more you can reduce the number of tests. Nevertheless, the procedure we're using, you define the technical commercial needs. So again, we had a few presentations about focusing on what the customer really wants rather than just selling commodities. It's important to understand more than what the customer wants or needs. It's more often sometimes the customer may not know what he could have. So it's a bit of an iterative process. So design the experiment and do the test, and we do it again and again. And what that means is you have a pre-screening set of tests, you then have the main customization set of tests, and then you have the verification tests. And guess what? We're in the field, all of you guys are working in, waiting for 28 days at least. So you're doing a round of tests, plus a bit of organising time, repeating. So it's taking about 5 months to customise one product. So we don't do it lightly. We're not going to do it for a $10,000 opportunity. It's for big cement plants, big producers, where we can try and get down. There's value for us, and it's worthwhile doing for the cement plant. And it's proving to some extent. So we don't apply it everywhere. But I'll just go through this example to finish off. This was a CEM 3 CEM 4, I think, very high, low clinker factors. So it was very high SCMs, and barely giving a 32.5. So the blank cement was giving 7 at 1 day and 32.5 at 28 days. And you can see the target to make a CEM 32.5 class cement, but it was requiring a 50% increase in the early strength and a 15% at 28 days. So the next 4, CB1104, the CBC1276, the ESE223 and the TDA, these are all, if you like, already existing traditional additives using our different technologies. The first used a higher alkanolamine technology that we patented about 20 years ago. The ESE is a modified alkanolamine that we work with one of the major chemical producers to synthesize, and the TDA is a very traditional old, using common chemicals. And they more or less did what we expect them to do. Some of them gave good early strength, some of them gave good late strength, but none of them could reach the targets. And then the next XR607 and 525 are coming out of the second phase of the customization. Both were pretty much getting, the XR525 was hitting the target now for the early strength, but still not on the late strength. And the final additive that came out of this was XR632, which has been commercialised. The dosage there, for those familiar with our chemicals, is quite high. We're normally working at 300-400 grams per tonne. That's 300 to 400 parts per million, up to about 2,000. This is 3,000, although now it's physically been in use for 2 years, and I think they're using it about 1.5, so 1,500 grams per tonne. It's brought the costs down, some of the benefits down, but it's all about that balance. It's easy to make the prediction of dose and cost, because we give a price, and the more they use, the more it costs per tonne of cement. But it's not so easy to assess the benefits, because it's not always a linear response. But that's an example of where, by systematic customisation, you could reach higher targets, and that's more or less, you know, the summary of where we've reached is, if you want very good results, you need to work a bit harder and customise. So we can also use this to evaluate new chemicals and synergies between chemicals, and synergies between the chemicals and the cements. And we're getting, you know, tailor-made additives for specific cements. It is demanding, so we're not going to apply it everywhere. But we are getting to achieve performances we didn't get before, and we're also getting it to achieve the same performance at lower cost. Basically, just try to formulate cost out of the system to give the same results. But it needs to be customised, but still allowing for variability in a cement plant. I mean, the cement producers will claim, you know, it's a very highly process-controlled industry, but it's using natural materials. There is variability within the cement plant. So if you really customise for one point in time, it's not going to be much good to a cement producer who has variability from minute to minute, hour to hour, and day to day. I think that was really my last slide to finish the day off. I'm not sure if it finished in the best way, Robert, but I'll let you be the judge of that.
That's brilliant, thank you. Are there any questions from the floor? I know that Mike was pretty thorough there. Okay, it's essentially a return on investment is the final question. Are you going to get the performance for the cost? And I think it's very, very interesting that it's a shame, unfortunately, we didn't have this presentation yesterday, because it would have been perfectly applicable to all of the topics yesterday. And I'd be very interested to see how your additives would perform in a tri-blend, quad-blend, you know, a very, very sophisticated mixture of materials. So that's something maybe for...
well, I mean, I'll give you the simple answer is, of course, they do, because we sell to those kind of cements, and probably customisation is even more important.
Right. But much more complicated to predict and to test for.
Yeah.
Okay. So finally, let's thank Mike once again. Thank you.